Alright, let's do another one. Today we're working on number 101, symmetric tree. Given the root of a tree, check if whether it is a mirror of itself, i.e. symmetric around its center. Interesting. Well, we could do this. We could do a level order traversal, what is effectively a BFS. And then after we do this, we can say that basically check if the list is reversible, or not reversible, is a palindrome. Let's see. Null values, because in level order there's a chance that we don't have null values. Or sorry, there's a chance that we do have null values. This might be an expensive way of doing things, but we'll go ahead and do it for now. Because there's gonna be a lot of null leaf nodes, I tell you what. But null values can be given a value of, I don't know, like -101 because of the constraint of the problem. So this is like a iterative approach. We could also do some sort of recursive approach. And for that, I would argue that a node is, or rather a tree is symmetric if the left node, left child, if the left child of the left subtree is equal to the right child of the right subtree, and vice versa, right of left is equal to left of right, and so on and so forth. However, the question then becomes, well, what if we don't have a child? What if we don't have a child of that subtree, right? It's not as easy as, say, left is equal to right. That would be the same tree problem. What we want is a mirror or a symmetric tree. Maybe something else we could consider for a sort of traversal method, maybe not iterative, is that run a simultaneous post order and in order traversal. So this would be right focus, this would be left focus. If they have the same values, we're okay. And we also need to end at the root. That's how we know that the tree is symmetric. Otherwise, when the two iterator nodes, the two iterator references do meet and it's not on the root, then we know that there is something that is wrong. We know that there is some value which is null on one side and not null on the other in order for something like that to happen. I'm honestly not sure which approach I want to take. This recursive approach seems interesting. I just have to think about it some more because this seems, the recursive approach is usually just more succinct, which is what I like. We're gonna need left tree and a right tree. This would be to check the subtrees. Left tree dot left dot val is equal to right tree dot right dot val and left tree dot right dot val is equal to right tree dot left dot val. So those are the two conditions in order for something to be for a tree with for a tree with subchildren in order to be symmetric. Because at the root doesn't matter. The children of the root do. So we can say, so right now we would call is symmetric on the left and the right of the root. And this would proliferate down, 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 down until a level, let's see. We probably want an if, left tree dot, left is not null, or left tree dot right. Actually, no, that doesn't matter because this will just return null if that's the case. That's the beauty of it. In that case, we can say if left tree dot left is null and left tree right is null and right tree dot left is null and right tree dot right is null. Basically, if everything is null, gonna adjust it a little bit. If all of the subtrees are null, then what we will do is to return something different. In that case, we can return whether the left tree val is equal to right tree val. Otherwise, return is symmetric left tree dot question mark dot left right tree dot right and is symmetric of left tree dot right and right tree dot left. And now that I think about it, it very much just makes sense to have that. So if all of their children are null, then just return whether or not the values are the same. If the children are not null, if there are children that are not null, then we return whether or not they are the same. The problem in this case is that we need to stop this from proliferating even further and just repeating on null. We don't want it to recurse forever. Right tree is not null, or so actually what we can do now to think about it, left tree is null and right tree is not null, or left tree is not null and right tree is null. That's return false. If they're both null, return true. If they're both non-null, then return this is symmetric left and right. This is sorry. This is a little bit inefficient because of the fact that we will be wasting one cycle on the left and the right leaves. We can say that if left tree dot left, basically I want to say that if both of the children, or if all the children are null, then we also want to return, because basically we just don't want to add an additional layer of leaves to check in which they are all null, because even though that's fast, or not particularly slow, I guess, that's an additional layer that we have to check, and that's an exponential 2 to the however many leaf nodes we have to check, so that's bad. So it's better if we can check it here, that if the left tree's left is null and the left tree's right is null and the right tree left is null and the right tree right is null, then we can return true. So in this case, they are both non-null. Then we can just say left tree dot val right tree dot val. This is where the case where we are hitting here. So here, so we start at the root. We check if the left and the right are symmetric, and then they have children. They're both non-null. So then, and they have children that are non-null. So they are both non-null, and they are complete. And in this case, then we will say, we will pass it down further. In this case, we have 3 and 3. So in that case, we would return that. So now we are here. They both have null children. All of their children are null. So now we're comparing the values. So that would be the first comparison, is symmetric left tree dot left and the right tree dot right. And then the left tree dot right and the right tree dot left, we would also compare those. Both of those also have null children, have no children, so we compare the values. So both of those are the same. And left tree val tree val. So now as we go back up, we know that the left tree left is the same as the right tree right. The left tree right is the same as the right tree left, so that's fine. And additionally, we check the left trees, basically the middle nodes that we're at have the same value as well. We push that up, and then we go back to the original root node, and we return true. So this seems correct. This seems working. Let's check. Root.left, root.right. And we have to add question marks here because we don't know if they're... If one of them is if they have non-null on one of them. So for example, let's go to this one. We have 1. We go to the left and right. Left tree and right tree are not null. So we go to here. They have null children, so we return asymmetric left and right. In this case, the left tree left is going to be null. The right tree right is going to be non-null. So the left tree, so in this case, this would be null, this would be non-null. We return false. This would hopefully get short-circuited, and then we would proliferate that false all the way up again. So this is the recursive approach to it. Let's see if we need to adjust anything. And actually the entire point of this is to speed this up. We could get rid of this, but this would introduce the leaf problem. So let's run it on both of the sample problems, both of the samples. That seems fine. So let's throw it through the ringer and let's see if there's anything that we want to change. Okay, so we did it. However, the runtime is quite slow. 17.65% runtime and 10% space. That's a bit of a yikes. Let's see where we can improve. So, we have a root node. We're checking the left and the right are symmetric. This is symmetric, checks if the trees are null, if the values are null. And it also checks if they're both null. Basically, if one of them are null, then we return false. It's obviously false. If both of them are non-null, or if both of them are null, then it doesn't matter, we can return true. If all of the children on both sides of the tree are null, then we just need to check the current value. Otherwise, we check the left subtree of the left side and the right subtree of the right side, combined with the right subtree of the left side and the left subtree of the right side. Additionally, we also check the values of that we currently have. What we could do to potentially speed up this algorithm by a marginal amount is that we could try to short circuit this earlier by checking the individual values that we start with. Assuming that these are not the same, then we have no reason to go further down deep into the tree. And so at that point we would just stop. We can see if this is faster. I don't think it will be faster by a significant amount, but what we can see. Because this will catch most of the cases, I think, of a tree that is symmetric but not the same values. Basically that is complete, so all the nodes are, it's symmetric in terms of the nodes, it's just not symmetric in terms of the values, right? So this is something to consider. However, based on what I'm looking at right now for the symmetric thing, it doesn't seem like there's much that we can entirely speed up here. What I'm seeing is that we're checking all the possible nodes that we can. And so there's really not much in the way of, because in the worst case scenario, we have to check all the nodes. That's just the fact that we have to deal with. We kind of just have to check all the nodes in case something else pops up. So I'm really not sure how we can improve the speed in terms of this recursive approach any significant amount. I'm going to give it another submission to see if this actually changes anything, to see if the sort of bytecode, the Java bytecode that ends up being processed through Kotlin is actually any faster. I think my reasoning it makes sense, but I'm not too sure. So, yeah. And then we can maybe try out the iterative approach if we have time. So not an insignificant improvement. That was 33.72 versus what, 17%? 17%, right? But we see that a vast majority of submissions for Kotlin end up in the 260 to 280 range. We're just over the edge at 284, which is about here. Seems like there's another spike in terms of distribution here. I'm assuming that my solution is pretty similar to what other people have. This memory seems a little bit off, though, considering that everything is so skewed towards, what is that, 335? 35 megabytes of memory. We did shave off a little bit of memory and a little bit of runtime from that. But perhaps the solution of getting a good runtime on this problem is using an iterative approach. So we can start with the level order, BFS, and then we can see where we go from there. So we can set a initial node list is equal to list of tree node question mark with root inside. Let's say, well, this will be a mutable list of mutable list which contains tree nodes. And we'll slap root in there. We'll call this our layer list to have a better understanding of what it is. So it's a list of lists. Each list represents one layer. So while the layer list is not empty, we want to say a new layer list, or new layer, mutable list of tree node. We'll have a question mark in case we have a nullable tree node. And we can say that, let's see. I wonder if we can actually insert nulls into there and whether or not they'll count. We'll see. We can say var left reference is 0. Var right reference is equal to, and we'll need to grab our reference of a current layer. Layer list pop or get 0, and then we can say layer list at the end dot remove at 0. So remove our last our top element. Technically this would be more efficient as a stack, though Kotlin doesn't really have a native stack solution, though I guess we could probably use the Java one. I haven't actually tried that out before. Maybe that's something to experiment when I have time. Let's say the current layer dot size -1 is our right reference, while left reference is less than right reference. If left reference question mark dot val is not equal to right reference question mark dot val, return false. So if the values are not the same, or if one of them is null, then we just return false. Because if left reference is null, then this will just return null. In that case, we could probably just shave off some of this. Shave off some of this code then. Yeah, we could probably actually just get rid of the first two conditions. I'll quickly do that and see whether or not we actually get a faster time. It'd be funny if we did, like a one-liner change by getting rid of some, by doing some interesting logic. Because if I remember correctly, this should actually work. But we don't want that one either. Because this question mark dot would let us do some nullable stuff. Because if this doesn't pass, then it just returns null. And if there's a value here and not a value here, then null obviously is not equal to some number. I don't think this will actually be faster, though. It'd be funny if it was. Yeah, no, it's it's like slightly faster, but not significantly. The memory usage is much better, though. Memory usage seems like it's getting closer to the curve, but I don't know. Let's continue with our iterative solution. Let's see. Well, left references if not, okay. Then we can say left reference plus plus, right reference minus minus. Basic standard like is the list working properly. I'm just thinking about the layer, because it's 1 2 2 3 4 4 3. So this would get represented as 1 and 2 2. Then these two are equal. But how do we want to represent it? We want to first add the left one, then the right one. So this is left ref dot left, left ref dot right, right ref dot right, left, sorry, ref dot right, I think. But what if we went one layer down further? Ultimately, we kind of want these like little pods of size 4, don't we? Because we just want to check if those pods are the same each time. This feels almost divide and conquer-y. And perhaps it effectively is. Maybe in that case then, we'll make a new list. Val new quad mutable list of left reference dot left left reference dot right right reference dot left and right reference dot right. And then effectively we want to add that to our layer list, new quad. And this basically proliferates throughout our the rest of our system. This is effectively just an iterative way of explaining this recursive approach. It's effectively the same algorithm. We're checking the left of left with the right of right, then the left of right, and the right of left. So basically the same thing. If left reference left is null, and I'm just going to copy paste this. I'm adding in basically the same provision here. Just to make sure. So if all of them are null, then we just return or then we don't want to add anything. So we want to add, we actually want to negate this. So if any of these values are not null, then we run this expensive sequence. Otherwise, we don't care about adding in a new layer. Right? And if the values are not the same, then we just return false at that point. And we want to make sure that the current layer size is greater than 1. Otherwise, we might we run into the issue of then we run into the issue of potentially removing our or saying false at our root. So if current layer dot size is greater than 1, then we want to do that. Otherwise, we just really want to add the left reference left and the right reference else we just add, so layer list add mutable list of left or current layer 0 dot left, current layer 0 dot right. Basically, we just add in the children initially. Or what we can do instead is say that if root oh no, but we don't know if there's children. Oh, actually no. We just want to say if root dot left is null and root right is null, return true. Because then we don't want to deal. Because then we don't have to deal with the nonsense. And then we don't have to worry about this part. And we can get rid of this. So the layer size should always be the layer size will not maybe 1 still if it's a really imbalanced tree. But then we'd have a bunch of nulls. At least I'm assuming, I'm hoping that the sizes count for nulls, or at least rather, the sizes also count nulls. I may be wrong there, and this may be wrong then. But I think other than that, we don't need this new layer thing. And we can give it a shot. Let's give it a shot with our base code first, just in case we run into an issue and we have to unresolved left reference, well, right reference. Oh, right. Current layer. We need to wrap this around like that. Oh gosh. There's so much wrapping that we need to do. Around the indices. Okay. I think that's good. I think we're fine now. Return statement is... Oh, right. If we don't find any discrepancies, then we just return true. Looks like we have a TLE. That's not good. We could add that. That might fix the issue. I just spotted that weird typo. Okay. Looks like our first case worked. Basically, this is just an iterative solution, or an iterative rendition of my recursive approach, where I use sort of a list of lists. This doesn't seem any faster. It seems like it uses more space because we're using more in place. But again, I guess the recursive stack is also something to keep in mind. That also takes up space. Well, let's see. So this is a corner case. So we ultimately didn't do that. And we don't want to give null values any special. Right, we're fine there. Sorry, I was just thinking whether or not we need to add something else if we could add something else to make it speed up a little bit more. I'm just gonna submit this and see where we end up here for this one. I'm not very confident in this one, but we'll see. 292, yeah. So this is actually pretty much this is slower than our recursive approach. So the additional memory usage and the additional, I guess, headroom from the Kotlin side of the collections probably does add up also. So I think I'm fine with where it's at. I did this essentially recursively and iteratively, basically running the same approach, but still I think it's a perfectly fine approach. The speed is something to take a double look at, but again, I do know that it can be a little bit weird, LeetCode, in terms of ranking your submissions, and sometimes things just run faster and sometimes things just run slower. But maybe this is something to reconsider as well. Like I said, I'm not great at something like binary trees as much as I want to, so this might be something to reconsider taking a look at in the future. But I think I'm fine with it as it is currently, so I'm going to leave this here. But in any case, that's all for tonight, and I hope you learned something, and I'll see you for the next problem.